Hey everybody, let's look at the electrochemical cell problem that we were supposed to do and see what we can figure out. So they give us this reaction where we have zinc and oxygen making zinc oxide. And the first question says, using the data in the table above, calculate the cell potential for the zinc air cell. So we know that E for the cell is still going to be E for the cathode minus E for the anode. And we know the cathode is the one that's reduced and the anode is the one that's oxidized. So we have to look on our half reaction table and figure out what's going on there. If you look at the overall equation, we know zinc is going from 0 to +2. So the zinc is being oxidized. And then the oxygen is going to go from 0 to -2. So the O2 is going to be reduced. So we know the O2 is the cathode and the zinc is the anode. So we can look at our reduction potential for our O2, and that is 0.34. And then we can subtract that from the other one. The zinc electrode is a -1.31. And so if we do that, then we get a E cell of a positive 1.65 volts. So this is going to be spontaneous. It will create a current, and we can use that as a battery. In the second question, it says, the electrolyte paste contains OH minus ions on the diagram. Draw an arrow to show the direction of migration of the ions through the cell. So we have a picture that has this with the paste, and so the O2 is over here, and then our metal is over here, and it tells us that the electrons are coming in this way. So the electrons are flowing through the wire like so, and that means the OH minus ions are going to go in the same direction. So you should have them moving over towards the metal, or to the left on that picture. Let's see. It says a fresh air zinc cell is weighed, and then they use it for a while, and they want to know what happens to the mass. Well, typically in a battery, everything is in a closed system. So electrons move through the wire, ions travel through the salt bridge, but everything that's there is still there. It might go from an atom to an ion or an ion to an atom, but it's all self-contained, so the mass doesn't change. In this particular cell, the oxygen comes from the air and then ends up making zinc oxide, which camps out in our cell. So we're adding oxygen to this system from the outside. So therefore, our mass is going to go up as the system runs because we're adding oxygen all the time. So for part B there, you want to say that the mass increases. In 2, I just did that. You want to talk about the reaction and how this oxygen comes from the air. And so our product has mass in it from the O that we didn't have in the cell to start with. So that's why the mass is going to go up. In part C, they say that you're going to take this up to the top of a mountain, and they want to know what's going to happen to the cell potential. Well, you can think of this in terms of Le Chatelier's principle. So as we go higher up the mountain, the concentration of oxygen in the air will decrease. And anytime you lower the reactants concentrations, then you're going to slow down the overall reaction. And so you're going to make less products. And since this voltage is a product, then we know that the E of the cell will go down as the oxygen concentration goes down. in part D, they ask about two different possibilities for electrodes, sodium and calcium, and they want to know which one's going to transfer more electrons. Well, if you look at them in your reduction potential list, we have Na2O, and then we also have CaO. But if you look at the reduction potentials, both of those involve the production of two electrons. So each one is going to use its own kind of thing there. Well, actually, this is one sodium to one electron, and then this is one calcium to two electrons. So we really just need to do some stoichiometry here and figure out how many moles of each there are, and then how many moles of electrons there are going to be. So let's take a look at the sodium. So they give us a gram of sodium. And we know that we can change that to moles by dividing by the molar mass. And then we also know that because there's two NAs in that half reaction, Na2O, and that gives us 2 moles of electrons, we can say, look, we're going to get 2 moles of electrons for the 2 NAs that are in our substance. And so that's the number of moles of electrons from the sodium. But if we do that same thing with calcium, now we need to divide by the molar mass of Ca, which is, I don't know, right around 40. 40.08, something like that. And then here we know that I get 2 moles of electrons for every 1 mole of calcium based on the stoichiometry. So that's going to give us 0.050 moles of electrons. So the calcium one is slightly better. There are 2 factors, the molar mass and then the ratio of electrons. So that's the one you want to choose, and there's the reasoning. Then for part E, they ask us to do an electron configuration for zinc. Now zinc is at the end of the 3D section. So if I make a little space to write this out, going back to our electron configurations, we know that zinc is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. That's what it is for a zinc atom. Now, when a zinc atom turns into a zinc ion, it loses 2 electrons. Typically, we would take them away from the outermost energy level, but in this case, we see that we have a filled D shell. So the rule for the stability of a filled shell is that you actually remove the 4s electrons, leaving those empty, so that the 3d electrons can stay full. So we would say that we're taking them away from the 4s sublevel because of the stability of a filled shell. Or shield in this case, apparently. So you get a point for the electron configuration and a point for saying that in this case the electrons come from the 4s sublevel. So hopefully that helps. You can total up the number of points you have and then check to see how you did if you want. Once you get the idea, you can run through that and try them again. You've got a KSP problem coming up due next, and so I'll work on scoring guidelines for that here real soon. See you then.